So here you can see we have applied the Amperes law to determine the magnetic field of the solenoid, which is a current carrying solenoid. So the closed line integral of B dot dl is equal to mu naught times the total current enclosed by the Amperian loop ABCD. So this side can be split into these four terms, which is B dot dl for the line segment AB, plus this is B dot dl for the other line segment BC, then B dot dl for the line segment CD, and finally B dot dl for the line segment DA. And this is equal to mu naught times the total current enclosed by the Amperian loop. Now what is this N over L? If L is the total length of the solenoid and N is the total number of turns in that solenoid, then N over L will give us the number of turns per unit length. And this is Li, which is the current carried by the solenoid. This is the current carried by the solenoid in the region which is enclosed by the Amperian loop. This much current will be enclosed by the Amperian loop, that is N over L times Li. Now here we have AB equal to CD equal to L, the length of the rectangle, but there we had H, so let us denote this length by H. In the diagram we represented it by H. So this first term is referring to the line integral of B along the segment AB. Just to recall, this was your line segment AB having the length H. So the line integral of this AB, which is B dot dl, will be B into H, because AB is parallel to B and both are making an angle of 0. That is, this line segment AB and the magnetic field B are parallel and are making an angle of 0 with each other. So the contribution to the line integral of B would be equal to B times H. Here once again to remind you, CD is out of the solenoid, so magnetic field B over here is 0. So the contribution to the line integral will also be equal to 0. Here these two segments, that is BC and AD, are perpendicular to the magnetic field. So B dot dl for both the segment will be equal to 0, because B dl cos of 90 gives you 0. So B dl cos of 0 for the segment AB, B dl cos of 90 for the segment BC, plus 0 because this was for the segment CD, which was lying outside the solenoid where B was equal to 0. So we are writing 0 for that part. Next is B dot dl for the segment DA, which was also at right angles to the magnetic field. DA was making an angle of 90 degrees, so here we are writing B dl cos of 90, and this is equal to mu naught times N over L Li. Cos of 0 is 1, cos of 90 is 0, so substituting 0 over here, we get just this term, B dl cos of 0 is 1, and dl from A to B is equal to the length H of that segment. So let us write H over here as well. You can write L as well, but since we have denoted that side by H in our diagram, so that is why we are writing BH is equal to this thing, mu naught times the total current enclosed by the Amperian loop. So if we represent this thing, that is the number of turns per unit length by the small n, then we can write it as B is equal to mu naught times the small n into I. Actually, this small l is the length h. This one is the length h. So this h times I actually gives you the current which is enclosed by the Amperian loop. That is why we are multiplying it with the length times the current carried. We will not multiply this mu naught by the total current which is carried by the solenoid. We will multiply it with only that current which is enclosed by the Amperian loop, and the Amperian loop has the length h, so h times I is enclosed by the Amperian loop. So we will have B is equal to mu naught times n into I, where I will be the current carried by the solenoid and enclosed by the Amperian loop. This would be the general form of your Amperes law as applied to the solenoid. So this integral which gives you the length of the line segment AB will be replaced by h over here, and similarly here we are also having h. Next we will determine the field due to a toroid. Now in the figure you can see a toroid, and you can see that it is actually a solenoid which is curled in the shape of a ring. So you can see that solenoid which is twisted or turned or wound in form of a ring gives you a toroid, and it is carrying a current I. So we have to determine the magnetic field due to this current carrying toroid. Now when the solenoid was straight, that is, it was not in form of a ring, then its field was in form of straight line. Now if you curl this thing in form of ring, then it along with the solenoid, its field lines will also be twisted in form of rings. If you curl this or give a shape of a ring to this solenoid, then the magnetic field lines which are straight in this case will also be bent in form of rings along with this solenoid. So that is why here you can see that the magnetic field lines are curled, or they are in form of a ring over here instead of straight lines, just as was the case for the solenoid. So let us apply the Ampere's law to determine the field due to solenoid.